Today we're going to be looking at a geometric interpretation of determinants. Specifically, we're going to be looking at determinants as size functions. So let's say that we have some pair of linearly independent vectors. So in R2, let's say that we have two linearly independent vectors. And so from these two vectors, v and w, we can form a parallelogram here. We could form a box just by taking parallel copies of your vectors and forming this box here. And then similarly, you could do the same thing in any dimension. So if you're in R3, maybe you have three vectors, u, v, and w. You could take a bunch of parallel copies of u, v, and w, and you could form a box this way. So the question is there an easy way to figure out the area or volume of these objects? So first things first, the box formed by a set of vectors v1 through vn, you can also think of this as the set of linear combinations of v1 through vn, except all of the coefficients, t1 through tn, all have to be between 0 and 1. So, for example, let's look at the two-dimensional case here. So we have v and w. So this set would be like t1v plus t2w. So right here, we could think of this as just being 0w plus v, and this would be 0v plus w, and this vector right here would be w plus v. Well, sorry, like this point up here would be w plus v, because that's our, let me sort of draw that real quick. So this right here would represent the vector w plus v, and then I could look at w plus like half of v, and that would be this vector right here, and then maybe you have v plus half of w would lie somewhere up here. And so that's sort of what I mean when I say that we can think of this this box as being equal to this set right here. Okay. So the idea that I want to explore today is that the size, by size I mean like for 2 dimensions it would be area, for 3 dimensions it would be volume, but like so we're just going to call this the size of the box formed by these vectors. And we're going to say that the size of the box formed by these vectors is equal to the determinant of the matrix obtained by taking these vectors and putting them into a matrix. And I want to show you why exactly that would be true. By the way, doesn't matter if you use v1 through vn, the vectors, as columns or as rows, because the determinant of both of those matrices that you get by interpreting v1 through vn as rows or columns, those would just be transposes of each other, and the determinant of a matrix and the determinant of its transpose are equal, as we talked about previously. Okay. So here's the idea for how we're going to show that the area or volume of the box is equal to the determinant of the corresponding matrix. The way we're going to do it is we're just going to say, hey, determinant functions satisfy 4 properties. Let's interpret the size function as being just another function of matrices. So now we can just think of the size of the box as just being the size of the corresponding matrix, and show that that size function satisfies the 4 determinant properties. So for the first property of determinants, we need to show that if a row reduces to b by multiplying a row by a scalar, then the determinant of the new matrix is k times the determinant of the previous. So here's a 2-dimensional picture of what's going on here. So here I'm just doing the two-dimensional picture where I have v and w, and the shaded in blue is the box formed by it. And over here, I replace w with a scalar multiple of w. And so my I don't like blue. And over here, so the blue and the W combine is the new area of this box that I'm forming, this parallelogram. And the area of the blue plus the W is equal to 1.5 times the area of the blue. And so this is just like a, a simple example of how this could happen here. So this property is satisfied. If I scale one of my vectors, then that would scale the entire area or volume for boxes by the same factor. So this first property of determinants is satisfied by the size function being area or volume or whatever. So that first one is okay. That one works. All right, let's do the second one. If let me not scroll down too fast. So if I do a row reduction by multiplying, by adding a scalar multiple of one row and adding that to a different row, then the determinant of my new matrix is the same as the determinant of the matrix I had before. So this does not change my matrix. Here's a picture, a two-dimensional picture of what's going on here. So starting with v and w, and I'm replacing v with v plus a scalar multiple of w here. So here I'm subtracting half of w, and what do I get here? So let's maybe what's going on here? So here is v, right? So if this is v, then half of w, maybe I can do this. So half of w would be something like that, and maybe I'll move it here so that I can just move it along with us. So that's roughly what half of w is. And I'm taking the vector v and I'm adding half of w to it, and that takes me from that blue vector to this vector right here. Okay, so this vector right here is my new v plus negative half w, and the area of this box, well, how can I compute the area of this box? Well, this is a parallelogram, and parallelograms, the formula for area of a parallelogram can be given by the base times the height. And so the slant height does not actually matter at all. The only thing that actually matters is the height, which is formed by taking a line which is perpendicular to your base and drawing that to the other side of the parallelogram. And so taking v plus scalar multiple of w does not change this height at all, and so the area is still going to be the base times that same height in all cases, no matter what our scalar is, and thus my size is going to remain unchanged by doing this. So size functions satisfy the second property, and so now we now have 2 of the 4 properties. Technically, we have 3 of the 4 properties because the third property turns out is actually redundant. You could show that the third one falls out. It is a consequence of the previous ones. However, we're not gonna show that. We're just gonna show it directly that it's still satisfied. And this one's a little bit weird because you have to interpret things in the right way. So this one says that if I were to swap 2 rows, between matrices, then my determinants of these matrices should differ by a negative sign. So, how do we interpret that here with this picture? Because if I switch V with W, well, like, I'm not changing my box at all, right? My box is still formed by the vectors V and W, even if I switch the order of V and W, because V and W are still there. Nothing really happens with that. So it seems like, oh, my area should remain unchanged. Why is it changing by a minus sign? Well, the answer is we can actually interpret area as being a signed area. And so what I mean by that is, well, let's say that W is first in our ordering of these vectors and V is second in our ordering. Then we would go from W to V in a counterclockwise way. And because we're going counterclockwise, we will say that this counterclockwise reading is giving us a positive area, whereas if I had V first in my ordering and W second, then I would go from V to W clockwise instead of counterclockwise, and clockwise we say is going to be a negative, is going to correspond to a negative area. And you could make sense of this for three-dimensional boxes as well. And so I don't really want to get into exactly the geometric interpretation of that, but you could figure out what the signed area is by looking at the determinants of these matrices, as we'll see soon. But I don't want to get, you can interpret it in the in a similar way to this two-dimensional version, but I don't want to get too hung up on that detail. I just want you to understand that size functions do actually satisfy this this third property of determinants. Okay. And our fourth one is that the determinant of the identity matrix is equal to 1. So the corresponding statement for size functions would just be, well, look at the unit box. So I guess you could look at the, let's do the two-dimensional 1x1 square. Right, if all of these side lengths are 1, then the area of this one is going to be 1 square unit. And so the fourth property should also be held. By the way, I want to think of this as like the vector 1, 0, and then this would be the vector 0, 1, etc. So in particular, you would have this vector first and then this vector second, so that you're reading counterclockwise, so that you get the positive area. Because if you put them as rows or columns, you would get the identity matrix. Okay, cool. So that one works. Therefore, all four determinant properties are satisfied by our size function, and therefore we can interpret the volume or area of a box formed by vectors, as we described prior, as just being the determinant that you get by putting all of those corresponding vectors into a matrix. And again, it does not matter if you put them in as rows or as columns, because you could still get the same you will still get the same determinant in either case, because those two matrices are just transposes of each other, and transposes have the same determinant. Excuse me. All right, so let's just do a quick example. Let's find the area of this box right here. So here I have the vectors given as rows. So I have -4, 4, and I have 5, 2. This is certainly not drawn to scale, but So if I didn't know that I could use determinants to do this, how would you actually go about doing it? Well, I guess you could figure out, based off of this vector, you could figure out what the length of this vector is equal to. So once you figure out that length, then you could figure out the height of this parallelogram, so you have to draw the perpendicular, a perpendicular line from one end of the parallelogram to the other end. But that seems pretty annoying and hard to do, right? Whereas now that we know that we can just do this using determinants, I can just throw this stuff into a matrix and take a determinant. So let's put negative 4, 4, and 5, 2 into a matrix. And then what's going to happen here, by the way, if you notice, I'm doing the wrong order, but it's anyway. Let's see what we get. So if I take the determinant, I would get negative 4 times 2, which is negative 8, minus 4 times 5, which is 20. So this would be negative 28. Note that it's excuse me. Note that it is a negative answer that we're getting here. And for area, we probably want a positive area, right? And in fact, the way that I set up this matrix, I read from this matrix, from this vector to this vector, so I'm going clockwise. So if I do clockwise, I should expect to get a negative area, whereas if I were to do the vector 5, 2 first, and then negative 4, 4, then I should get 5 times 4 minus 2 times negative 4, and then this does give us our positive area. Okay, cool. So if you start with this vector first and then go counterclockwise, then you will get your positive area. Also note that I could have interpreted the vectors as columns, and I would get the exact same thing. So here I'm interpreting 5, 2 as a column and negative 4, 4 as a column, and so my determinant here would be, again, 20 minus negative 4 times 2, which is, again, 28. So nothing is changing here. So the area of this parallelogram, which if we didn't know how to use determinants to do this, would be pretty time-consuming and tedious to figure that out. We could just take the determinant of a matrix and just do it that way, and it just works out. So I think that's a really nice application of that, and this geometric interpretation I think is pretty neat.